Hey folks, today we're going to talk about radioactivity. Now, radioactivity is a section we didn't do during the chemistry unit because I wanted a chance to go back onto this topic from after we'd finished off earth science and looked at biology as well, so we can make some connections. Now, radioactivity starts with the same sorts of things we did in chemistry. And so right at the beginning of chemistry, we were looking at each element and looking at the components of the elements, talking about their internal structure and their subatomic particles. So just see how much of this you remember. And if you find this really tricky, pause the video and look back at your notes from chemistry to remind yourself of this material. Now let's take an element. Let's take, say, carbon. If you look at the periodic table, it looks something like this. Carbon in the center. We've got its atomic number in the top left, its atomic mass on the bottom, and then we have its charges, if there are any, in the top right. And from this, at least in chemistry, what we did is we found the number of protons, the number of neutrons, and the number of electrons. Well, in chemistry, what we really spent our time looking at was just protons and electrons. Neutrons were only there as, I describe them as glue. The idea that protons, they are really positive, but being positive all the time kind of makes enemies of the people around you. So protons don't like each other. So something has to also be present in the nucleus to keep them stuck together. Otherwise, two protons pushed in close proximity would shove each other apart. So the neutrons, because they're neutral, act like a glue. All the positive charges are attracted to the neutral charges of the neutrons. Now this is a large-scale way of representing something that is much, much smaller than our macroscopic world, but the idea is still the same. So in chemistry, what we did is we looked at the idea of atoms, which had equal protons, and I'm going to say protons as P and electrons as E, equal numbers of protons and equal numbers of electrons. And the reason that they were considered atoms at that point was that when the protons, which were our, we'll use orange for this, positive charges, and our electrons, which were our negative charges, were balanced, there was no net charge. It was equal over the entire atom. Now we also talked already about ions. And ions was a situation wherein external conditions caused electrons to be either gained or lost from our atom. So if we gained electrons, that's gaining extra negative charges. And if we lost electrons, that means we've lost negative charges and more positive charges remain. And so ions was an unequal number of protons and electrons. Well, briefly, when we were in chemistry, we did discuss the third and final option for this. And this is the one that radioactivity is really tied to. And it's the third concept, which is isotopes. Now, isotopes this is where we're going to spend our time. Isotopes can be neutrally charged with equal protons and electrons. They can also become charged particles as ions, like we did for regular atoms. But an isotope is different because isotopes have a variation in the number of neutrons. So when we look at an atom, when you look at your periodic table, most of your atoms don't have a perfect exact value. They don't have an exact 0.0 number for their atomic mass. And the reason for that is that we're not breaking an atom up. We're not cutting the neutrons apart. We're not taking a proton and sawing it into pieces and saying, I'll put half of it here and leave the other half for some other atom. Every single individual atom is made up of whole numbers of protons, neutrons, and electrons. So we always will have an exact atomic mass that is a whole number. But these values are averages. And if we actually look at a periodic table like the one in the classroom, which has a higher precision to these values, what you get is a mass that looks more like this, 12.011. And the reason for that is that most carbon atoms have a mass of 12, 6 protons and 6 neutrons. But occasionally, we might have an additional isotope of carbon that has an extra neutron, or 2 extra neutrons. And those isotopes have different characteristics from the original atom. So what that means is that isotopes have a set of traits that are different from regular atoms and the ions we discussed in chemistry.